we often solve systems that have solution. But sometimes it may happen that a given equation has no solution. Fortunately for linear systems, we have a nice and clear theorem that tells us the condition which is sufficient and necessary for a system to have solution. And this is called Frobenius theorem. A system of linear algebraic equations, ax is equal to b, has solution. If and only if the rank of the matrix of the coefficients is equal to the rank of the augmented matrix. This can be illustrated by the following system. We have seen many systems that have solution. Now let's have a look at one system that has no solution. Consider the system x plus 3y is 7 and x plus 3y is 8. Yeah, it's obvious that if the left-hand side agree, the right-hand side should agree as well. If they don't, no solution. Because x plus 3y being anything, it cannot be simultaneously 7 and 8. So this has obviously no solution. But let me take this example as an illustration of this theorem. So if we write the augmented matrix, then we have 1, 3, 7, 1, 3, 8. And to find the rank of both the matrix and the augmented matrix, we can operate this as a whole, and we want to use Gauss elimination to bring the matrix to the upper triangular form. So we have non-zero here, so we can write 1, 3, 7. And to get 0 here, we take the second row and we subtract the first one. Then we have 0, 0, 1. Well, and this matrix has rank equal to 1, because this is a 0 row, so the rank is equal to the rank of the 1 by 2 matrix. While the augmented matrix has rank 2, because we have 2 linearly independent rows. So you see, in this case, rank of the augmented matrix was 2, rank of the matrix was 1, they differ, so we have no solution. If the rank is the same, then the system has a solution, but this theorem alone does not tell anything about the number of solutions, whether there is just one solution or infinitely many solutions. So, if the ranks agree, it has solution. If the rank of the augmented matrix is greater, it has no solution. And what if the rank of A is, on the other hand, greater than the rank of the augmented matrix? Stop me for a moment and think it over. Yeah, I'm back again. This cannot happen. This cannot occur. This is not possible. If you take a matrix and it has some rank, then adding one extra column, any numbers, may increase the rank if you add something new. Or it may remain the same if you add a column that was already there. Or if you add a column that is multiple of a column that is already there. Or if you add a column that is a linear combination of the columns that were already there. So if you add something that can be built from the previous columns, the rank is the same. And if you add something new, which cannot be constructed as a linear combination of the previous columns, the rank goes up, but it cannot go down. Well, and this approach actually proves the theorem, because you see, this relation means that x is a vector of coefficients, and these coefficients multiply individual columns of the matrix. So what is on the left is just a linear combination of the columns of the matrix A, with the vector x arrow being the vector of the coefficients. So this is a linear combination of the vector of the columns. And if it is equal to B, that means the vector B, the right hand side, is a linear combination of the columns that are already there. So the rank is the same. But if the rank is higher, then B is something new. Something new meaning it cannot be constructed as a linear combination, so it cannot be equal to some linear combination of the columns of the matrix A. Well, to illustrate that this is a linear combination of the columns, let's consider the following matrix: 2, 3, 4, 5 times xy. This is 2x plus 3y and 4x plus 5y. But this can be also written as x times the first column, 2, 4, plus y times the second column, 3, 5. Because this is 2x, 3y, 4x, 5y. You see? And if you perform this multiplication and add, you get exactly this result. So, matrix times a column vector is a linear combination of the columns. This is the first column, this is the second column. Here you have some coefficients, and you add them. So this is a linear combination of the existing columns of the matrix. So this is a very useful approach, very useful understanding of this expression. So that was the Frobenius theorem that tells us whether a linear system of equation has solution. And it tells us that it has solution if and only if the rank of the matrix is equal to the rank of the augmented matrix.